The pond initially contains 1,000 litres of unpolluted water, and the pond's leaking at a constant rate of 20 litres per day. It's suspected that contaminated water flows into the pond at a constant rate of 25 litres per day, and that the contaminated water contains 2 grams of pollutant in every litres of water. Well, that means there's a constant rate of 25 litres, that actually 50 grams are being added every day. So in fact, I'm going to write that at this point. dx in by dt is going to be 50. It's assumed that the pollutant instantly dissolves throughout the pond upon entry. This is going to be relevant for when it's leaking out, and it's given that there are X grams of the pollutant in the pond after T days. Okay, I've kind of already referenced that. And we're asked to show the situation can be modeled by this differential equation. So I've already dealt with the amount going in. It's all about the amount going out, and that is the trickiest bit by far. But what I said, I looked at the concentration. So the concentration of pollutant after 0 days is going to be, well, there's none at the very start because we're told it's unpolluted. So it's going to be 0 divided by 1,000 because there's 1,000 litres in total. Then after 1 day, well, we've got some coming in, of course. We've got 50 coming in, but we've also got some going out. So we can't say it's 50. It's going to be some amount, X, and then we're going to be dividing by, well, there's 20 flowing out, there's 25 flowing in. So actually, there's going to be 5, an extra 5 after day 1. And if we now look at T days, then it's going to be X over 1,000 plus 5T. T is the number of days, it's 5 every day. So after 2 days, there'll be 1,010 litres of water and so on. And then we can use that with the fact that 20 litres is flowing out each day. So therefore, dx out by dt, the rate of change, is going to be, well, it's minus because it's flowing out. And then it's going to be this 20 multiplied by the concentration of pollutant. So 20 times x over 1,000 plus 5t. So that can then be written as minus 20x over 1,000 plus 5t. And if I divide top and bottom through by 5, we'll get minus 4x over 200 plus t, which is what we have over there. So therefore, dx by dt is going to be the sum of those together, 50 minus 4x over 200 plus t. And that is enough, enough written work to derive that equation. Now, don't stress if you struggled with that. Just practice them. They will be coming up. But the thing is, you can still solve it. All right. You can, as long as you can get some credit, that's the main thing. And you will improve over time. Just keep going with it. So hence, find the number of grams of pollutant in the pond after 8 days. Well, let's get the general solution. And then we're going to need the particular solution. And then we can sub in t equals 8. Okay, this is a first order differential equation. And it's in the form dy by dx plus px y equals qx. I know I've got x and t instead, but that's like the general form that we learn about. And the thing is, what we do to deal with this is times by an integrating factor, which is e to the integral of px. That will allow us to absorb the two left-hand terms into like a single derivative. So let's get it in that form in our case. dx by dt plus 4 over 200 plus t. That's my equivalent of p of x multiplied by x is equal to 50. So my integrating factor is going to be e to the power of the integral of 4 over 200 plus t, which is then e to the 4 ln 200 plus t. But I can bring that 4 up, and then I can undo the log, so I've got e to the ln, so it will become 200 plus t to the 4. And that is what I'm going to multiply through by. So this will give me 200 plus t to the 4 plus 4, got the dx by dt, pretty important, dx by dt plus 4, 200 plus t cubed, and then of course you must also multiply the 50 by that. Okay, we can write this left-hand side as d by dt of x times by 200 plus t to the 4. And you can check it if you use the product rule and differentiate x and keep that the same. You get the first term, keep x the same. I've just realized I actually missed an x out, sorry. But keep x the same times by the derivative of 200 plus t to the 4. That is that bit there. So it's all good. And that is equal to 50, 200 plus t to the 4. And I'm ready to integrate now. So integrate both sides with respect to t, because the left-hand side just becomes x times 200 plus t to the 4. On the right-hand side, I'm going to be dividing through by 5 when I raise the power, so I'm going to get 10 times 200 plus t to the 5. If you differentiate that back, we'll get back to what we had here. But don't forget your plus c, absolutely essential, because x is then going to equal 10 times just 200 plus t to the power of 1, but plus c over 200 plus t to the 4. Okay, and yeah, we could even multiply that out. 2000 plus 10t plus c over 200 plus t to the 4. Right, well, what are we told? That at the very beginning, there's 1,000 liters of unpolluted water, which means when t is 0, x is 0, because there's no pollutant. Let's sub in. 0 is then going to equal 2,000 plus c over 200 to the 4. If we solve that, we get c, actually you get it in standard form, c equals minus 3.2 times 10 to the 12. That is what it is. Which means x, particular solution, to be fair, that was our general solution, is then going to equal 2000 plus 10t minus 3.2 times 10 to the 12 over 200 plus t to the 4. So when t equals 8, sub it all in, and we get 370.391, or 370 grams. Brilliant. Then C says, explain how the model could be refined, i.e. what is it not including that, or what are some assumptions made that we could maybe improve upon? I think I went down the wrong, well, my answer's not in the mark scheme, but actually I think it's okay. So I took a look at the particular solution and then said, as t approaches infinity, well, we're going to get a fixed term here, but this is also going to tend to infinity. And this here is going to approach 0. But what that means is that x is going to just get bigger and bigger. So I said, as t approaches infinity, x approaches infinity in a linear way. And we need to have a limiting factor brought in to stop that happening, because of course it can't approach infinity in reality. It wasn't in the mark scheme, but I'm feeling like that would be okay. What the mark scheme is looking for is that the model should take into account the fact that pollutant does not dissolve throughout the pond upon entry, like instantaneously. or that the rate of leaking could be made to vary with the volume of water in the pond. But I think there's lots of answers you can give here, so mine should be absolutely fine. I'm just saying these are the ones the Marks King gave as well. All right, well done.